Welcome you all to module 15, which will be about movement generating function. So this movement generating function is kind of a transform of a random variable which will help us in generating the movements. So let me introduce what does a movement generating function of a random variable x means. So suppose x is a discrete or absolutely continuous random variable, and suppose fx is its PMF or PDF. Now I define the set Ax to be collection of all those t belonging to R such that expected value of e to power tx is finite. Note that this e to power tx is always greater than or equal to 0, so this is same as saying that this is collection of all those t belonging to R for which expected value of e to power tx exists, right? Because this would be same as saying that expected value of mod of e to power tx is finite. So Ax is collection of all those t's such that expected value of e to power tx is finite. Now one thing is clear, that if I look at the point 0, 0 is clearly there in Ax, because expected value of e to power 0x is expected value of 1, which is always finite. So 0 is always there in Ax, so Ax is always non-empty. So now I define the movement generating function. So the movement generating function of a random variable x is defined by mxt, which is expected value of e to power tx. And of course, Ax is a set where this quantity is finite, so I allow t to vary only over Ax. So this quantity is called the movement generating function of a random variable x. Now one thing is clear, mx0 is 1, that is what we have seen, because your mxt is expected value of e to power tx. So mx0 would be expected value of e to power 0 into x, which is expected value of 1, so mx0 is 1. Another thing is e to power tx is always positive, strictly positive. So mxt would always be greater than 0, because exponential is always greater than or equal to 0, and in fact since x is real valued, it would always be strictly greater than 0 for every t belonging to Ax. So these are the two properties which movement generating function possesses. Now suppose you know the movement generating function of x, and you want to know what is the relationship of movement generating function of x with that of movement generating function of cx plus d, where c and d are some constants. So that is what we will try to see over here. So suppose y is a random variable which is cx plus d for some real constant c and d. Let us look at the movement generating function of y, which is expected value of e to power ty, which is same as expected value of e to power t, y is same as cx plus d. Now this becomes, the inside the expectation, this becomes e to power td into e to power tcx. But d is constant, t is constant, so e to power td will go outside, so this becomes expected value of e to power ctx. And what is this? This is a movement generating function of x at the point ct. So this becomes e to power td into movement generating function of x at the point ct. Now note that mxt was finite if t was belonging to Ax. So mxct would be finite if ct belongs to Ax. So that is why your t has to be in Ay, which is collection of all those x belonging to C, such that x belongs to Ax. Now why the name movement generating function is given to this transform is from the fact that it helps us in generating the movements of random variable x, which would be clear in the next result. So it will help us in generating the movements of a random variable x, and that is the reason why it is called the movement generating function. So let us try to see how it helps us in generating the movements of a random variable. So suppose h is a given positive constant, and suppose mxt is finite for every t in minus h to h. So what it says is, suppose your movement generating function is finite in a neighborhood of 0, because minus h to h is a neighborhood around 0. So suppose movement generating function is finite in a neighborhood of 0. Then I can get many interesting things. So the first result which I get is, then you can differentiate movement generating function any number of times. Not only that, the second says, if such a thing happens, that means movement generating function is finite in a neighborhood of 0, then movements of all order exist. So mu r prime is equal to expected value of x to the power r is finite for any r in 1, 2, 3 and so on. Not only that, you can get this rth moment by differentiating the moment generating function r times and putting t is equal to 0. So very interesting. So you can see how powerful moment generating function can be to derive the moments. So if these conditions hold, then the rth moment you can get just by differentiating the moment generating function r times and putting t is equal to 0. Not only that, if this assumption holds, that means moment generating function is finite in a neighborhood of 0, then it has Maclaurin series expansion, which can be written as summation r is equal to 0 to infinity t to the power r by factorial r mu r prime. So this also suggests that if you can expand mxt in the Maclaurin series expansion, which will always exist because provided mxt is finite for every t in minus h to h, then if you look at the Maclaurin series expansion of mxt, mu r prime is nothing but coefficient of t to the power r by factorial r. So that is how you can get the mu r prime. So rth moment is nothing but coefficient of t to the power r by factorial r in the Maclaurin series expansion of moment generating function. So very nice result. So if you have to get the moments from moment generating function, one way is you differentiate it r times, put t is equal to 0, and then you get the rth moment. Other thing is you look at the Maclaurin series expansion, and then look at the coefficient of t to the power r by factorial r, then the quantity which you get as a coefficient is nothing but rth moment of random variable x. I will try to give just an outline of proof. I will not give a very rigorous proof. So let us consider the absolutely continuous case. So I fix r belonging to 1, 2 and so on. So mxt is expected value of e to the power tx, which is integral e to the power tx fxx dx. I try to look at d to the power r mxt by dtr, which is same as this. One can do it recursively. First one finds it for first derivative. Then under the assumptions, it can be justified that you can take this differential operator inside the integral sign, and that is what you have to do. This would require some sophisticated mathematical arguments, which I am not going to elaborate over here, but under the given conditions that your moment generating function exists in a neighborhood of 0, this is allowed. So now if I look at dr by dtr e to the power tx, that becomes x to the power r e to the power tx fxx dx. Now I put t is equal to 0. When you put t is equal to 0, t is equal to 0 is put over here, and then you get quantity 1. So the thing which you get is minus infinity to infinity x to the power r fxx dx, which is nothing but mu r prime. So as I said before, where the passing of this sign over here can be justified through advanced mathematical arguments, which I am not going to touch in this course. Now let us consider the second part, Maclaurin series expansion. So mxt is same as minus infinity to infinity e to the power tx fxx dx. Now I expand e to the power tx in Maclaurin series as Maclaurin series, so it becomes summation r is equal to 0 to infinity tx to the power r by factorial r. That is the expansion of e to the power tx. Now t is constant, r is constant, so I take this sum outside. Again, that requires a little bit sophisticated mathematical arguments, which again I will not do it over here, but under the assumption that moment generating function exists in a neighborhood of 0, this can be justified, that this sum you can take outside. And that is what I do. Summation r is equal to 0 to infinity, t is constant, t to the power r by factorial r is constant, and then minus infinity to infinity x to the power r fxx dx. And that becomes summation r is equal to 0 to infinity t to the power r by factorial r mu r prime for r is equal to 1 to so on. So now we will see some examples. First, let us consider one corollary of this result. Under the notations and assumptions of above result, which is basically saying that moment generating function exists in a neighborhood of 0, let us define psi xt to be log of mxt. Then you can differentiate psi x once and put t is equal to 0. The quantity which you will get is nothing but mu 1 prime. You can differentiate psi x twice and put t is equal to 0, the quantity which you get is mu 2. Note that if you differentiate moment generating function twice and put t is equal to 0, you get the second moment, which is expected value of x square. So if you put mx2 0, that is expected value of x square. And expected value of x square, you know, is same as variance of x plus expected value of x whole square. So to get a variance of x, you'll have to further subtract expected value of x whole square from here. But it says if you have to get the variance directly, you can look at this psi xt, differentiate it twice, put t is equal to 0, you can directly get the variance. So the proof is simple. I try to differentiate psi xt. Psi x1t is 1 upon mxt into mx1t. That was the psi xt. Psi x10 is mx0 into mx10. mx10 we have seen is nothing but mu1 prime, and mx0 we know is 1. So that gives me mu1 prime. So I have got the first derivative of psi x. I look at the second derivative. So I differentiate this once. So that becomes mxt square, then mxt, derivative of mx1t, which is mx2t, minus mx1t into derivative of mxt, which is mx1t, and that is how you get mx1t whole square. I put t is equal to 0, psi x to 0, then you get mx0. mx0 is 1. This quantity is 1. Then mx2 0, which comes over here, minus mx10 whole square, divided by mx0 is 1, so that is why you get just this quantity. And mx20 you know is expected value of x square. mx10 you know is expected value of x, so that becomes whole square. And that is what you get over here, so which is same as mu2 prime minus mu1 prime whole square, which is nothing but variance of x. Now this function psi xt in the textbooks is called the cumulant generating function of x, because it generates quantities which in many textbooks are called cumulants, and that is the reason why psi xt is called a cumulant generating function. So I am not going to define what cumulant means, because that may not be of direct significance in this course. So for r is equal to 1, 2, so on, let us look at mu r prime, which is nothing but coefficient of t to power r by factorial r in Maclaurin series expansion of mxt. That is what I explained a few moments back. So now I am equipped with finding the moments using the moment generating function.